this video, I will be talking about addition reactions to alkenes. I will go through all the different types of addition reactions, their mechanisms, and also Markonikov's rule. So the first reaction is the catalytic hydrogenation, which is the addition of hydrogen in presence of a catalyst. The catalyst can either be palladium on carbon or can be something like platinum oxide. In this reaction, the hydrogen will add to the double bond to give you the corresponding alkane, which is the alkane with the same number of carbon atoms. The role of the catalyst is to lower the activation energy of the reaction. So if you look at the energy profile for the uncatalyzed pathway compared to the catalyzed pathway, you're going to find that the activation energy is lower in case of the catalyzed pathway. So the catalyst here will make the reaction go faster because it lowers the activation energy. In the absence of the catalyst, the reaction will not take place. So hydrogen with an alkene in the absence of the catalyst will not react. The second reaction is the electrophilic addition. So in case of electrophilic addition, you have an alkene which has a double bond here. The double bond between the two carbon atoms is electron rich and it acts as a nucleophile. While you have the polar reagent where there are two atoms bonded together, they have a difference in their electronegativity. So one atom will have a partial positive charge while the other one will have a partial negative charge. In this case, the atom with the partial positive charge will act as an electrophile. In this reaction, the two parts of the polar reagents will be added to the double bond to give you the substituted alkane. In this reaction, the electrophile here will act as a Lewis acid and it reacts as an electron pair acceptor. And the reaction here also, the alkene will act as an electron pair donor or as a Lewis base. Here it acts as a nucleophile. Let's have a closer look at the mechanism of this reaction. So the hydrohalogenation, which is the addition of HX or the addition of hydrogen halides. So when you have something like a reaction between an alkene and hydrogen chloride, the hydrogen will have a partial positive charge here and the chloride will have a partial negative charge. The first step in the reaction is the attack of the nucleophile, which is the double bond of the carbon-carbon atom, towards the electrophile, which is the hydrogen with the partial positive charge, while the bond between the chlorine and the hydrogen breaks. When the hydrogen is added to one of the two carbons, that will generate a positive charge on the other carbon. So that will generate a carbocation. The chloride that left from the first step will then attack the carbocation to give you the final product, which is the chloroalkane. Now let's talk about Markonikov rule. So Markonikov's rule talks about the addition of the hydrogen halides to unsymmetric alkene. So when an unsymmetrically substituted alkene reacts with hydrogen halides, the hydrogen will add to the carbon that has the greater number of hydrogens, while the halogen will add to the carbon that has the fewer hydrogens. So let's have a closer look at this reaction. So this is a reaction between propene and hydrogen bromide. In propene, you can see that the double bond between carbon number 1 and carbon number 2 generate an unsymmetric alkene because the first carbon has two hydrogen while the second carbon of the double bond has one hydrogen and one methyl group. The first step in the reaction will be the attack of the nucleophile towards the electrophile, which is the hydrogen of the hydrogen bromide. So the hydrogen can either add to carbon number 1 or to carbon number 2. So if the hydrogen adds to carbon number 2 here, that will generate a positive charge on carbon number 1. And the carbocation here is a primary carbocation. The second possibility is the hydrogen attacking the first carbon. So it adds to the first carbon and that will generate the positive charge on the carbon number 2 and now we have a secondary carbocation. So remember that primary carbocation will be less stable than the secondary carbocation, which is the more stable. So we have two possible intermediates. One of them is more stable than the other one. So here the hydrogen ion or the hydrogen plus will add to the less substituted carbon, because that's going to generate the more stable carbocation. Less substituted carbon means the carbon which has the greater number of hydrogen ions. So now when the bromide attack the first carbocation and the first one, that will generate one bromopropane, which is the minor product, because this is the product that comes from the less stable carbocation. In the other case, when the bromide attack the secondary carbocation, that will give you 2-bromopropane, which is the major product, because this is the product that comes from the more stable carbocation. So this is Markonikov rule in case of addition of an to unsymmetric alkene. When we look at the reaction kinetics, you can find that more highly substituted double bonds are more electron rich, and the reaction will proceed faster than the less substituted one. While in case of hydrogen halides, the reactivity will increase with the acid strength. So the more acidic or the more highly acidic the hydrogen halides, then the faster the reaction. Hydrogen iodide is more acidic or the most acidic out of the all hydrogen halides. So the reaction with hydrogen iodide will proceed faster than hydrogen bromide, and then hydrogen fluoride, which is the least acidic, it will be the slowest reaction. So you can see that more substituted alkenes will react faster, and hydrogen iodide as well will react faster. Hydration and dehydration. This is another addition of a polar reagent. So it's in this case we would use an acid catalyst. The reaction doesn't proceed without an acid catalyst. Hydration and dehydration are the reverse to each other, and both of these reactions will need an acid catalyst. So the acid catalyzed hydration of an alkene and the acid catalyzed dehydration of alcohols are the reverse reactions to each other. So you can either get an alkene from an alcohol through dehydration, or you can get an alcohol from an alkene by hydration. So let's have a look at this reaction. Now we are adding the water molecule in presence of an acid catalyst to an alkene. Let's have a closer look at the mechanism of the reaction, and don't forget the Markonikov rule as well. So this is the alkene we have here, which is 2-methylpropene. This is an unsymmetric alkene, and then the reaction starts by the addition of the acid catalyst. The nucleophile, which is the double bond of the alkene, will attack the hydrogen with the positive charge or the acid. This reaction is reversible, so don't forget these two arrows here to refer to the reversible reaction. The hydrogen will add itself to the carbon, which has the highest number of hydrogen atoms. This is to follow the Markonikov rule. So carbon number 1 here has 2 hydrogens, while carbon number 2 has 2 methyl groups. So the hydrogen will be added to the first carbon. So will be hydrogen, 3 hydrogens here, and then 2 methyl group on carbon number 2, and that will generate the tertiary carbocation. If the hydrogen adds to carbon number 2, then that will generate a primary carbocation, which is much less stable than the tertiary carbocation that is generated here. And then you have the water, which is the nucleophile now in the reaction mixture, and it will attack the carbon, which is the with the positive charge, or the carbocation, and that will give you the alcohol now. So you're gonna have CH3, and then CH3, CH3, and then you have the OH. Of course, the hydrogen will leave here from the oxygen, so will regenerate the acid, which is the catalyst. So this is the final product of this reaction. Will you get the tertiary butyl alcohol rather than getting the primary alcohol? The following reaction is the halogenation, which is the addition of halogens. So the halogens here that can be added are either bromine or chlorine. Fluorine is very violent reaction and normally it's not used, and iodine will not react. So when we add halogen, we add either bromine or chlorine. Their action proceed more or less in the same mechanism, but the intermediate is a bit different. So when you have an alkene like this one, and notice that this is also an symmetric alkene, and you have a bromine, when the bromine will the presence of the alkene and the bromine, there will be an induced dipole in the bromine, where one of the two bromides will have a partial positive charge and the other one will have a partial negative charge. The nucleophile, which is the double bond, will attack the partial positive bromine and the other one will leave. Please notice the type of solvent that we use here. This is a nonpolar solvent, carbon tetrachloride. In presence of carbon tetrachloride, we're going to have a specific product, but if we use polar solvent, the product will be different. So in this case, the first step, when we add the bromide, we're going to generate an intermediate. The intermediate here is a bit different than the previous reactions, where the bromide that is added will form an intermediate with a cyclic structure called the bromonium ion. The bromonium ion then is attacked by the other bromide with a negative charge, and you need to notice two things here. We're still going to apply the Markonikov rule. Well, the bromide with the negative charge will attack the carbon which is more substituted, or the bromide will attack the carbon which has the lowest number of hydrogen atoms, because this is a more stable carbocation here if we break the bond between the carbon and the bromide and the bromonium ion. So the product here is going to be the dibromo 1,2-dibromo alkane. However, this type of addition is called anti-addition because the bromide will attack from the back side of the presence of the other bromide on the intermediate. So there is an anti-attack to the most hindered carbon, or the carbon which is most substituted. Another example, you can see the addition of chlorine to this 1-methyl cyclohexene. This is also going to be an anti-attack, and it's going to add the other chloride with the negative charge to the most hindered carbon. We're going to apply the Markonikov rule. So the first intermediate is going to be the chloronium ion, where it gives you this cyclic structure, and then the other chloride will attack the carbon which is the most substituted carbon here to apply the Markonikov rule or follow the Markonikov rule, and that will give you the anti-addition product. So as you can see that the two chlorides are not on the same plane, but they are in opposite planes. So the product here is the anti or the trans addition, not the cis addition. In the previous slide, I talked about the addition of halogens, and I said that if you add the halogen in presence of nonpolar solvent, you're going to get the 1,2-dihalogenated alkane. However, if you use the polar solvent like water, you're going to get a different product. So if we add water with bromine, if we added bromine in presence of water as a solvent to the double bond, you're going to get the halohydrine. You're not going to get the dibromo product. So let's have a closer look at the reaction mechanism. So the mechanism of the halohydrine formation, the first step is going to be exactly the same. So the halogen will add to the double bond, and here, as we can see, that it will give you the halonium ion. If it's bromine, it's going to be bromonium ion. If it's chlorine, it's going to be chlorinium ion. This is the intermediate with the cyclic structure. And then the second step is instead of the halide attacking the carbon or the carbocation, we have the water, which is the polar solvent here, is the one that is going to attack the carbon. In this case, OH will be added. The attack again is going to be anti or backside attack, the same way as we have seen with the halogens. And then the final product is going to be called halohydrine, or we added an OH and then the halide on the other carbon rather than adding two halides. So the solvent plays a major role here in the product that is